The next item is the John Blake University Teaching Medal for 2023. And the IMA is delighted to announce Professor Chris Sangwin of the University of Edinburgh is the winner of the 2023 John Blake University Teaching Medal. John, it's the John Blake. Chris, I'll ask you to come up in a second, but let me just read the citation. The John Blake University Teaching Medal was introduced in 2020 and is awarded to an individual in recognition of their significant and sustained contribution to the teaching of mathematical sciences at university level. Professor Sangwin is Professor of Technology Enhanced Science Education in the School of Mathematics at the University of Edinburgh. He previously worked in the Mathematics Education Centre of Loughborough University, the University of Birmingham, and the UK Maths and Stats and OR Network, the MSOR. He was awarded a National Teaching Fellowship in 2006. He's known internationally for his work on computer-aided assessment, including the development of a mathematics e-assessment system, STACK, system for teaching and assessment using a computer algebra kernel. STACK is now widely used in universities across the UK and internationally, and indeed at my institution. STACK saw a significant increase in use during the COVID-19 pandemic, as mathematicians urgently needed a way to support students studying remotely. STACK is currently supporting the learning of a diverse body of students at over 1,500 sites across 6 continents and has been translated into over 20 languages. It is used by a commercial textbook publisher, physics curriculum and instruction, to provide online support to their learners. Chris's work is grounded in research and scholarship. In developing STACK, Chris has thought deeply about the nature of teaching, learning and assessment in mathematics, often referring to historical teaching texts and basing his thinking firmly in the educational literature. He is the author of a number of books, including Computer-Aided Assessment of Mathematics and the popular science book, How Round is Your Circle, which illustrates and investigates many links between mathematics and engineering using physical models. It is a testament to John Blake's legacy that as director of the MSOR network, it was he who appointed Chris to the network in 2000 as a research fellow with a remit to research and promote effective teaching of higher education mathematics within the UK. Professor Sangwin is an inspiring teacher and an internationally recognised leader in the field of mathematics assessment, and in particular computer-based assessment. He has had significant influence on mathematics teaching and learning at many universities within the UK and overseas. His work has inspired and enhanced the learning of tens of thousands of students across the world. For this reason, he is a worthy winner of the 2023 John Blake University Teaching Medal. Chris. So, wrapped up. Thank you. Congratulations, really well deserved. So Chris is now going to give a talk. Have we got everything lined up? So this will be about, is it half an hour? What we told? 1840. Yeah, 35 minutes. Oh, right. I have to pass across as a. Oh, you've got one.
Yeah, wide for sound. Thanks, everyone. I've decided to choose the title "Why I'm Not Too Worried About AI" as the subject of my talk because I'm getting asked a lot. A lot of people are just quite blunt. Chris, surely this means it's the end of your software when AI can just do everything. And so I thought we'd just address that head on today. But before I get into that, thank you. Thank you, everybody. Thank you to my family who are here. Thank you to my colleagues. Thank you to John Blake, who appointed me. Thank you to the IMA. Thank you to my students, and so on. So thank you, everybody, and thank you for coming this evening. I thought it'd be fun to start with some very recent news. Monday, there's now a $10 million prize for an AI that will gain a gold medal in the International Maths Olympiad. Right? That's now the goal of AI research as of Monday. I've no doubt that will happen. I'm sort of working on the assumption that that will happen, and yet still I'm not too worried about that, as I'll go on to explain. So let's start here, Hound and the Hare. A hound starts in pursuit of a hare at a distance of 30 of his own leaps from her. He takes 5 leaps while she takes 6, but covers as much ground in 2 as she in 3. In how many leaps of each? So, has anyone seen this problem before? No? Anyone seen anything like it? Must have seen something like it. Okay. So I academically inherited this book, Examples in Algebra by Tukey, 1904. And for some reason, there are a lot of good things in this book. It's a lovely little book. This problem jumped out at me for no reason as I was reading it, and I've used it a lot. And then about a decade later, I found out from this history that this is actually a very famous problem. It's actually in the first European version is Alcuin of York, AD 790, in Problems to Sharpen the Youth. Right? So Alcuin's a fascinating character. He was, I think, if I remember rightly, he ended up in Charlemagne's court. He travelled all around Europe. He wrote widely and was a leading scholar of the time. Some of you may remember the goat, the cabbage, and the wolf crossing the river problem. Have you seen that one? That's in this book as well, right? So I think he wrote that problem. But actually, it goes back even further. It goes back to basically the same hound and the hare problem goes back even further to ancient China, according to Sweats. And you can imagine people were trading problems as they're going up and down the Silk Road, talking to each other, challenging each other with problems and puzzles and all the rest of it. So I think mathematical problems and puzzles are artifacts. We should take care of them. I think they have a history, they have an important cultural significance. And as a discipline, we often attribute theorems, De Moivre's theorem, we remember who, not that they're always named after the right person, of course, but that's a whole different talk. But nevertheless, we don't look after puzzles and problems in quite the same way. But they're enduringly popular. Nearly the whole population likes puzzles. It doesn't matter. These are not talking necessarily about things that are only at the far end of research at all. So there's this scale of a Sudoku in a newspaper right the way up to an Olympiad problem or a research problem. I just don't see any hard boundary. And I think if we are going to continue to teach mathematics and value mathematics in an AI age, we need to value that whole spectrum, right? And I really, really think that's important. So I think of these kinds of famous puzzles as like the mathematical equivalent of a poem, a verse. And each generation should learn them and struggle with them and whatever. Because ultimately, I think we want our students to be well-versed. That's a compliment, right? And by struggling with these puzzles and learning them yourself and doing them yourself, you become experienced, practiced, skilled, knowledgeable, and so on. Okay, so here's another one. Arthur is pro-Brexit and Cameron is pro-Remain. Arthur shakes his fist at Boris and Boris shakes his fist at Cameron. Okay? Prove that a Brexiteer shakes his fist at a Remainer. Right. Okay, that's the puzzle. Okay, so I'm just going to do what mathematicians do, and that's just get rid of some of the noise, because it's hard. That's the first step, isn't it? Get rid of some of the noise. We've got A for Arthur, who's a Brexiteer. We don't know whether Boris is Remain or Brexit. Cameron is a Remainer. And we're trying to match this pattern, aren't we? We want a Brexiteer to be pointing at a Remainer. That's what we have to prove. And so there are two cases. Boris is either Remain or Brexit. So if Boris is Remain, then Arthur's shaking his fist at Boris and we're done. If Boris is Brexit, then Boris is shaking his fist at Cameron and we're done. So in every possibility we're done, but we don't actually know which one happens. Okay? That's slightly weird. We can prove that something happens without knowing how it happens. And you think this is just a silly puzzle, but actually I don't think it's a silly puzzle at all. I think it's a very useful pattern of thought. So if you want to prove that an irrational power of an irrational number can be rational, then we're going to use this same pattern of thought. So a rational number just means we can write it as a fraction. And it's somewhat surprising that not every number can be written as a fraction, just in sort of bald terms. But root 2 is a very famous example. You can't write that as a fraction. And so we're going to, like pulling a rabbit out of a hat, mathematicians say, I'll consider this. And so we're going to consider, root 2 to the root 2. Now, I would be very surprised if you could write root 2 to the root 2 as a fraction. I mean, it just, my mathematical experience and my mathematical sense says that's just unlikely, okay? But it could be rational, and if it was rational, then we would be done, because an irrational power of an irrational number is rational. On the other hand, if it's not rational, then we'll just take another root 2 power and do a little bit of algebra, and we get 2, which is 2 over 1 is a fraction, it's a rational number. So this is exactly the same pattern of thought that is used in the silly puzzle as in the maths. And that's what mathematicians do. I mean, there are not that many really valuable different intellectual moves when you start organizing knowledge and seeing the same arguments coming again and again. And we need to recycle them, and you need to remember them and organize them, and that's the nature of education, isn't it? So when we look at patterns, there are a number of patterns that we use in mathematics. The pattern of two loci is a geometrical way of breaking a problem down and then recombining it. We have superposition, we have recursion, and we have the Cartesian pattern. And these legitimate patterns of thought become what we consider to be acceptable mathematical proofs. And Pollier's How to Solve It is a book which I really like, but his other books, he's written Induction and Analogy. These patterns come from his other book, Mathematical Discovery. I think these books are just superb, and I recommend them to anyone who hasn't read them. I'm not going to talk about these patterns. I'll just talk a little bit about the Cartesian pattern. So this comes from Descartes' Rules for the Direction of the Mind, a good title. And here, so Descartes says we should reduce any kind of problem to a mathematical problem. I think that seems reasonable. And then we should reduce any mathematical problem to algebra. Well, forgive Descartes, that is his contribution of algebratizing geometry, and coordinates is part of turning algebra into geometry. So he's going to reduce it to algebra. And then reduce any algebra problem to a single equation and solve, and we're done. That's the Cartesian pattern. And Pollier's very wry about this. He just says, the more you know, the more gaps you see in this project. Well, that's fair enough. But what I want to say today is that actually solving the equation is only the last step in all of this. So the actual mechanical process of that is only just one part of the whole pattern of thought. We have to set up the equation, we have to interpret the solutions, and sometimes we have to reject some solutions because they're not physically realistic. So all of that is part of this. This is a kind of unglamorous end of education. These were my exam scripts from 2017. And you can see why people want to use technology to mark the work, right? It's not very glamorous. It's repetitive. Any task that requires repetitive work from anybody, even especially experts, we want to try and automate that. And recently, colleagues in Kenya are using my software, and this is not my summer, right? I'm well supported in Edinburgh, but other colleagues in other places have a very different experience of teaching. So it's quite natural that we're going to use technology to solve some of those problems in education. But at the end of the day, the tool is a means to an end. I'm not writing this software because I want to write the software. I'm writing the software because I've got a job I want to do. And ultimately underpinning all of that is that we need tests worth teaching to. This is Hugh Burkhardt at Nottingham, for whom I have a huge amount of respect. And so I am sure at some point my software will be superseded, probably by something better. That is the inevitable lesson from educational technology. And I think I'm, my first computer had 1 kilobyte of memory. I was in the schools in the 1980s when Logo came along in the BBC Micro. So thank you, Celia, for all your work on that. I'm the product of that. I've grown up with computers. They have come along in my generation. And when you look back at all the educational technology that's come and gone, I'm sure that will happen. So I want to make sure that I'm trying to focus on the thing that really matters, which are the things that students do and what they learn through that. That's ultimately the most important part. So So this is why I'm not too worried about AI, really. I'm really not. Actually, I'm very excited about it, but that's a different part of it. Because whatever happens, you still have to understand what comes out of the machine. If it suggests something to you, this is irrational, you need to know what that means. And AI might help you understand what that means, but you still need to situate what the AI tells you in what you already know. So there's no shortcut to that. And then there's a basic pleasure from solving a problem. There is, and everybody knows that. That's not going to go away. There are computers that beat nearly everybody in chess and Go, and people still play chess and Go. We should have the same view on mathematics, I think. And then you get recognition from your peers. If you do something difficult, people respect you for it. That's true in sport, it's true in drama and literature, and I think it will continue to be true in maths. So that could be an Olympiad medal, that could be a school exam, could be a whole range of ways that we recognise people who've achieved something, and I don't think that's going to go away. Of course, you could cheat and use an AI, but again, that's about how we set up those systems to make sure that it is the person doing the work. And then there's the importance of aesthetics and value, which I think this is something that we will have a lot more opportunity to discuss. If AI helps us reduce the need for repetitive work within the subject, and there will be things we throw away from the subject, no doubt, then perhaps we can concentrate on aesthetics and value judgments. And I find elementary mathematics endlessly fascinating. I don't think there's any shortage of that, even at the elementary end of the subject at all. This is not about just the, of course it exists at the advanced research. That's why people like advanced research in maths. Of course it does, but it also exists in the elementary side of the subject. For those people who haven't done any maths research, it's not actually difficult to come up with a novel theorem. Okay? It's just not. If you just choose large numbers and do something with them, the chances are nobody's done that before. You can prove something, and formally speaking, you have some novelty. But nobody's going to be very impressed by this, are they, really? They might be a little bit more impressed if you realise it's not quite so obvious and there's something interesting about this. But this actually comes from what I think is still the shortest maths paper ever published. A direct search on this computer yielded this weird observation as the smallest instance in which 4 fifth powers sum to a fifth power. This is a counterexample to a conjecture of Euler that at least n nth powers are required to sum to an nth power. So suddenly we're in really good company now. I'd be very delighted if I found a counterexample to a conjecture by Euler, one of the greatest mathematicians ever. So value judgments and aesthetics and all these things matter a lot to the subject. And it may be that AIs start to suggest value judgments, but I'm not sure that's going to happen in the near future. And I think humans are very well placed to decide on these things. So again, for these kinds of reasons, I'm not at all worried about AI. But just to give you a sense of why I'm enduringly fascinated with elementary mathematics, and I don't think there's any shortage, I'm going to talk about the area of a plane triangle. Okay, right? I think that would be a good place to start. So the area of a plane triangle is half base times height. Yep. And a couple of years ago, I came across a fascinating paper by Baker in 1885. And he lists over 120 different formulae for the area of a triangle. This is a snapshot from his paper. He doesn't prove any of them, he just lists them all. And you actually have to get to formula 38. His first formula just uses the side lengths. The height is not the most obvious thing. You don't always get given the height. So you might just get given the 3 lengths of the sides of the triangle, and that's where he starts. And he sorts them all out and arranges them. But you have to get to 38, and then you keep going, and it's this one, 73, right? This is his formula for the area of a triangle, SR. And that, I think, is the simplest one in his list, because there's no numerical constant, and it only uses 2 letters. So all these letters relate to different things in the triangle. So what are R and S? Well, S is half of the length of the perimeter. Okay, so it's called the semi-perimeter. So you have really got a numerical constant, it's just packaged up in S. So there is a numerical constant in there, but let's forget about that. And R is the radius of the largest circle you can draw inside the triangle. Yeah? Okay? So why on earth would the area of the triangle be half the perimeter multiplied by the radius? Okay, not entirely obvious. Well, let's just draw more triangles. Let's draw lots of right-angled triangles. Okay, so I've now drawn 6 right-angled triangles, and instead of A, B, and C, I've relabeled the side lengths. So we've got this side is X, and this side is Y. So we've got 2 triangles that are the same here, and 2 triangles that are the same here. So what we can do is we can just rearrange those triangles, and we've got a rectangle which is R times S, and then we're done. Okay? So I think that's beautiful. I think it's lovely. And it's interesting, I've been doing some research on the nature of proof, and I've been asking students and colleagues about the rigour in the subject. What is a rigorous proof? And in fact, rigour turns out to be a relative concept, and most of us agree on what is and isn't rigorous, in fact. And surprisingly, pictures are not inherently not rigorous. So professional mathematicians are quite happy to accept some pictures as being equally rigorous with algebraic arguments. Not always, but the idea that a picture is not rigorous doesn't stand up to research with real mathematicians. And I think this is perfectly rigorous. I mean, yeah. But it doesn't stop there, in fact, because when you've got a good idea, then we should carry on and see where we can get to with this good idea. Well, we can do the same thing with a square. Draw a circle inside a square. We need 8 triangles now, but we can do the same thing. Do the same thing with a hexagon. Okay, just keep going. You can do that same thing with any regular polygon, in fact. So let's just keep going and keep going and keep going. And those of you who know the history of how Archimedes found the area of a circle, he did that by approximating it by lots of polygons. So what is the area of a circle? Well, the length of the perimeter of a circle is 2 pi r, so S is pi r, and r is just r, because it's the largest circle you can fit inside a circle. And yeah, so that works as well. Yeah, so the same formula works. So immediately, a mathematician would ask, for what shapes does that formula hold? Right? I mean, it holds for more than the regular polygons. It holds for more than polygons. It's not true for all shapes, right? So what looks like a silly, trivial area of a triangle, we all know the area of a triangle, can be crafted into an interesting set of problems that takes you to what I would suggest is real mathematics, characterizing all the set of objects for which an interesting property holds. That's what maths is all about. So I'm endlessly fascinated about with elementary mathematics, and I think there's plenty more to be interested in. So we did this. I've taken over what's called an institute. John Mason and Anne Watson set up a mathematical institute, and every summer we get together. We limit it to 25 people, and we go to Ripon Cuddeston College near Oxford, and we get together and we just solve mathematical problems together. Right? That's what we do. And it's Jenny Back and Corinne Andrews and I have taken over from John Mason and Anne Watson, who've retired. They ran this institute for more than 20 years. There have been a whole range of mathematical topics. And for me as a teacher, the challenge is writing this sequence of problems. This summer, our topic was mathematical surprise. And we have a range of colleagues, from colleagues who only teach primary and never studied mathematics at university level, right up to people like me who only teach at university and have never taught in school. And we have a range of people who have a lot more experience than I do. So coming up with 9 sets of problems that are going to surprise that group of people is a certain intellectual challenge that I really like. And this area of a triangle seemed to be something that everyone could get started on, and that was a sequence of problems that I wrote for that. So it's all very well talking about problems and puzzles and Olympiads and all this kind of poems and all the rest of it, but the truth is, If you want to get good at something, it takes a lot of hard work. And this is just not very glamorous. It's just absolutely not very glamorous, right? And I'm convinced that if you want to become a good mathematician, you are going to need to learn a lot of algebra, and you are going to have number facts at your fingertips. However good the technology, you're going to have to notice patterns. This is poor Joseph Phillip. He's got 30.5 pounds of tobacco for £3, 12 shillings and 5 1/4 pence. And he is writing out his long division. There's just pages and pages of this beautiful handwriting, right? I mean, it's just amazing. And of course, a computer and a calculator was a profession. You had to get good at that because there was no alternative. So the one thing that I'm quite excited about AI is because it will give us an opportunity to have another conversation about what matters in our discipline and what doesn't and how we get there. And as a discipline, we've had those conversations before. We had them with computer algebra, we had them with calculators, we had them 400 years ago with slide rules. Right? So we're constantly having those discussions about what matters. Other disciplines may not have had that technology disruption before. I can't speak for other disciplines. Maybe they did in history, right? And maybe AI is going to write essays for you now and they haven't had to have those discussions. But as a discipline, we have had those discussions, and some of that discussion is relevant to what we're facing with AI now. And even with practice, even with what appears to be boring practice, I think with the design of interesting materials, we can design interesting materials even in situations which appear to be boring practice. In music, there's this idea of an etude, which is a study or technical exercise, but it's still a nice piece to play. That's the idea of an etude. And Colin Foster, a colleague for whom I have every respect for, has tried to develop this idea in a mathematical format. Let's have some practice that leads you somewhere interesting. And I think it's very useful to have names and to discuss the design of materials, having names for things like etude. No disrespect to Colin, but I don't think this is an entirely novel idea. I think teachers have been doing this for a very long time. Tukey was doing it in 1904. This is another set of exercises that jumped out of me on the page. Draw the graphs of x squared, minus x squared, 2x squared, x squared plus 2.5. Blah, 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 blah. Well, he kind of gives the game away here of where he's going, doesn't he? This looks like a set of boring exercises. In fact, they are highly structured and carefully designed, right? So, and this is why I like this book, because a lot of his things just appear to be pages and pages, a random page here, pages and pages of stuff without, when you just look at it, but a lot of it's like this. It's beautifully structured and very interesting. Plenty of other people have done things like this. I came across this book a couple of years ago, Crowder's Adventures in Algebra. So for Crowder, algebra is university year 1, proof that root 2 is irrational, proof there are infinitely many primes, those kinds of classical results. And here's a typical page in the book, page 99. It doesn't matter where we are. The point is that he asks you a question, and depending on your answer to the question, you go to a different page in the book. So again, in the 1980s, we had these fighting fantasy books. You're walking along a corridor, you see a troll, do you talk to it, fight it, or run away? I mean, it's that sort of thing, isn't it, right? And it's the mathematical equivalent of that 20 years earlier. I had a lot of fun reading this. I think the book is beautifully written, beautifully designed, and very interesting. And he's doing this with multiple choice questions. Now, I've written some sophisticated technology that tries to mark people's homework, but good design can do interesting things with very simple tools. We have very good tools now, right? So I think the actual design of the materials is what will endure. There's another one. Okay. And then I do want to mention these are advanced university books, but Bob Byrne has written 3 books, and for those people that haven't seen them, there is no text in these textbooks. They're just problems for people to do, right? And students find these textbooks particularly challenging because you do have to do everything yourself. That's quite a high bar. So, yeah, that's why I'm not too worried about AI. I think you still have to understand the stuff. You still want the pleasure of doing it for yourself. That is a basic human part of culture, part of who we are as human beings. And it is important to recognise other people. Thank you for recognising me today. But you know, that matters. But we have responsibilities to set up that recognition in ways that do actually correspond to something valuable, not just doing something because we've always done it. That's the challenge, isn't it? And part of that is acknowledging the importance of aesthetics and value judgments. So, thank you very much.
Thank you, Chris. Anyone? Questions? Yep.
The institution where I work, we're under pressure to reduce the dependence on formal exams. How do you see AI affecting the way we assess students?
Yeah. Well, if you really want to know that it's somebody whose name is on the degree certificate, then you have to have some checks to confirm it's their work. And the most efficient way to do that, to my mind, seems to be to get them all in the same room. Oral exams have all sorts of problems and biases that are well known, and they're very time-consuming to do. I mean, my linear algebra course now has 720 people. The idea that we would give them a half-hour viva doesn't seem to be that sensible. Of course, how many exams do we really need? And those are difficult questions. I don't think there's any alternative to something invigilated, really. But maybe I just lack imagination.
That's what we're being told.
Okay.
Can I urge you to moderate your comment about practice? Think about the way what lyrics come into your head when you're not thinking. Are they all good quality lyrics? There's something important about repetition which isn't high quality. It's part of the way we work. So clearly there's silly exercises, and Tuki's obviously much better than the average sort of rubbish. But repetition and practice are part of the show, and the idea that one can focus on the output. I mean, think of a pianist or a violinist. For them, the practice and are part of being a pianist. You can't take it away and just play serious stuff.
No, and there is some comfort in doing something that you can do and doing it well and repeating it. Absolutely.
Doing Sudoku, I mean, it's admirable.
Nothing wrong with that. And the point I want to make is that it isn't necessarily boring, and that you can have things like etudes that do go somewhere. That's the point I want to make. So yeah, I think we probably agree, Tony. Thank you.
Anyone else? Can I ask an ignorant question? I have a sort of memory that, and I think it was Arab mathematics, was meant to be written in verse. That there was a historical period where part of the way that you embodied the ideas was in the expression through verse or something like that. So your original thing about verse actually fitted into a tradition.
We would have to consult a better historian
yes,
than
anyone,
Does
Indian.
Does anyone know?
Could well be.
Interesting.
Yeah, but yeah, it may well have been that. Yeah. So that would add to your versification. But anyone else? I've got one other question, if I'm allowed. But so the other question is, with your interesting problems and the ones you showed where they were leading somewhere and they were getting, what happens to people who don't get it?
Yeah, I mean that's. But then. Well, okay, so the skill of the teacher is to devise enough hints, right? So when I use that puzzle with when I wrote up that observation about chopping up the triangle into 6 smaller triangles, the question, how much of a hint to go in that direction do you need to give? And that's the skill of a teacher, isn't it? Mm-hmm. Right? So if we want everyone to get there, then we would probably give more hints or walk around the class and drop a hint. If it's an Olympiad problem, you're not going to give so many hints because you really want to see who can do it on their own. So that does depend on the circumstance and the consequences and what you're trying to achieve, I think.
Any last question? Well, Chris, thank you very much.